Start record. Our next talk will be given by Evgen Shargorodsky from King's College London. Well, and you are working in Dresden as well? It's
yes, part-time and temporary.
Okay, so please go ahead. Okay,
thank you. Thanks to the organizers for inviting me, and congratulations to all students and faculty of Sinve staff on the occasion of 60th anniversary of Sinve staff. It's a great institution for which I have utmost respect, and I'm delighted to be here. Well, you probably might have noticed that out of 6 talks of this mini conference, 5 have tuplets in the title of in their titles. And had I known about this, there would have been 6. I would have spoken about tuplets operators, which are also dear to my heart. But I was told that I was asked to give a sort of colloquium type talk aimed at master and PhD students, and I decided to sort of opt for a talk that, I don't know, celebrates the unity of maths, so to speak, and it just felt was right for the occasion. So this will be something that basically the question itself is, one can say, in number theory, but it has connections to a variety, to a surprisingly wide variety of topics in maths, ranging from applied fluid dynamics all the way to logic. Right, this is a conjecture made by 2 mathematicians, Amick and Fraenkel. I never met Amick. He died in 1991, I think, of cancer, and he was very young. He was 39 years old. But I did know quite well Edward Fraenkel, and actually he was one of my mathematical heroes. You can see him in this picture, and he was a fine mathematician and true gentleman. Was really a special person. Now, the conjecture, look, I don't want to give you an impression that you will have a proof of this conjecture by the end of the talk. The conjecture is still open, and so I just want to avoid the situation described by Littlewood in his miscellany, where there was a paper that someone said at the beginning of the paper that the object of that paper was to prove something very important, and it transpired with great difficulty, and not till near the end that the object was an unachieved one. So I have not achieved the proof of this conjecture, so let me be very, very clear about this. So the conjecture is still open. Right, so the conjecture is about this simple equation. You can show this equation to school children, and with perhaps after some, I mean, you can explain what the conjecture is in like in 15 minutes to them, because it has something to do with linear independence. But so the interest in this equation comes from fluid dynamics, and there were quite a few papers where this equation was considered, and here is the paper by Amick and Fraenkel, where that conjecture that I have not stated yet, but I will, was first stated. And so, as I said, these papers were mostly in fluid dynamics journals, and I'm a pure mathematician, so these journals, Journal of Fluid Mechanics and Wave Motion, they're applied journals to me. But if you are more on the applied side, you might not think that these are applied, but even if this is your view, you'll still agree with me that ocean engineering is an applied journal. So the point I'm trying to make here is that so this equation was of interest to people who were publishing papers in applied journals. Now, it is connected to Stokes waves. And so what is a Stokes wave? First of all, we are in the 2-dimensional case. So the whole thing is not the physical reality of 3-dimensional space. You have a 2-dimensional model, And what you have is a steady periodic wave. You can see that sort of this is a periodic thing. So we have gravity there, and this is the wave propagates with constant speed. It is important that the depth of the fluid is infinite. So it doesn't really look like this in my picture, but this is infinite depth. It is important that it is an idealized fluid. It's an irrotational flow. I don't want to go into physics, which I know very little about, but for a mathematician, so irrotational flow, this is something that, and there is no viscosity here either. So this is something that basically lives in old-fashioned textbooks of complex analysis. In those textbooks, you always have a chapter on applications, and those are idealized fluids there. So this is that kind of model. And so this is the free surface of the wave. And it is determined by the just usual Laplace equation, which will be in the sort of fluid under the surface. And there is the boundary conditions are periodic in the horizontal direction. And at the boundary, we have a kinematic condition, meaning that this wave profile is a streamline of a particle. And also we have a dynamic boundary condition that says that the pressure in the flow should be constant. And this is just what it says is the atmospheric pressure is constant. Well, obviously it's not flat, there will be a minute difference between, say, atmospheric pressure here and here, but we can forget about this. We can assume that atmospheric pressure at that level is constant, and the pressure in the fluid is equal to that pressure. So this is Bernoulli theorem. And so in more mathematical terms, so we describe that curve, the wave profile, like this. So we have a curve in two-dimensional space. S is a parameter. You can think of this as, I don't know, time if you wish. It's probably not time. It's steady. Sorry, I take it back. No time. It's the horizontal coordinate, if you like. What we assume that it's kind of minimal assumptions. Minimal assumption makes sense. So first of all, that this should be an injective function. So you don't want the wave profile to make a loop. Okay, so it's just it should be non-self-intersecting. This is sort of perfectly natural assumption. This one just says that you have chosen a reasonable parametrization. So nothing specific. Here it simply says that as changes, the point in your curve moves. So this is just a question about parametrization. And our curve is periodic, and what this means that, I mean, you need to subtract this parameter here and say that this, the whole thing like this, is 2 pi periodic, because if you don't subtract this s here and say that without this minus s thing is periodic, what you are saying is that the curve is a closed one. So it's not what you want. You want it to be a periodic curve, and this is why you need to subtract minus s. So subtract s. So the curve we will call S capital, and the area, the domain below is omega, right? So just let me return to the picture. So this profile here is S, and the domain under it is omega. Okay, so, and here is the statement of the problem. So we need to find a profile. We need to find profile S such that for this domain under this profile omega, there exists a function which is harmonic in omega, which is 2 pi periodic in the horizontal direction. Now, this condition is, so we need boundary conditions in the boundaries, right? So in the horizontal direction, the domain stretches from -infinity to +infinity, and the periodicity that we have here is the boundary condition, if you like. Now we have the domain goes to minus infinity in the vertical direction. So we need a condition at minus infinity there, and this is the condition which roughly says that at the infinite depth, the flow doesn't feel the wave. So it goes, so this is the velocity, and roughly speaking. So, and that all it says that at the infinite depth, the flow moves at constant speed. Okay, so it's just an, again, physically motivated natural boundary condition there, but the main condition, of course, are on S, at our boundary. So, and there again, so let me come to the picture. So now, so I explained what happens in the horizontal direction. We have periodicity. I explained what happens as y goes to minus infinity. So the most important thing happen at this curve S, the profile. And here we have two boundary conditions, which say that the function, the harmonic function, is 0 there. And this combination that comes from Bernoulli constant pressure condition. So that this condition is satisfied. And mu here is a constant that is related to a so-called Froude number, something to do with fluid dynamics. Think of this just a constant parameter. Okay, so on S we have two boundary conditions. So which might be ringing the bell for you, because look, we just said that phi is 0 at the boundary, right? So therefore the tangential derivative of psi at the boundary is 0 as well, because the function itself is 0, so tangential derivative will be 0. So the gradient is simply the normal derivative. So this condition says that the square of the normal derivative equals 1 minus a constant, and y is the vertical coordinate. Okay, so this is a square of the normal derivative. Okay, you can square root both sides, and then you have the normal derivative is given. So on S you have two conditions: the Dirichlet condition and the Neumann condition, which looks like we have a heavily overdetermined problem. I mean, when you have the Laplace equation, you either have the Dirichlet condition or the Neumann condition, not both of them. So this looks like a strange problem. This looks like a very overdetermined problem, but it is not, because this problem would have been overdetermined if I told you what S was. If S is given, then yes, this is an overdetermined problem. But the problem is not about solving the boundary value problem in a sense. This is about finding S. So this is a free boundary problem. The main unknown in this problem, not psi that much, is this S here. We don't know S. And the idea is that can we find S such that if you solve, say, this boundary value problem with this condition, like Neumann type condition, then miraculously you have the homogeneous Dirichlet condition satisfied as well. So for most profiles, this is not going to be the case. But the question is, can we find a profile for which this actually happens? And this is the problem. This is the Stokes wave problem. And well, it was stated by Stokes. Now here there is slight inconsistency. I quote a sort of paper of Stokes in 1847, but he was in his 20s then, when he started looking at nonlinear wave with small amplitudes. Now this picture corresponds to later period in his life, and when he actually stated two famous Stokes conjectures, and they were stated in 1880. Now the first conjecture is that there exists a large amplitude wave such that the wave profile is not a smooth curve, it has angles. And so something like this happens. So the existence of a profile that solves that free boundary problem such that we have an angle, and this angle is 120 degrees. So the existence of the wave profile of this kind, and this is called the Stokes wave of extreme form. The main difficulty here is proving the existence of a profile with an angle. If you assume this, then 120 degrees is not a big problem. So it's not about proving that there exists an angle of 120 degrees and not 117 degrees. No, it's about proving that there is a profile with an angle. And if you assume that, as I said, 120 degrees is an easier part. So this is the first conjecture. And he was certain that the answer is yes. And he had kind of an ansatz where there was kind of infinite angle. So he was convinced, I think he believed that that was the case. But the second conjecture, he was not sure whether this is true or not. So he asked basically question, is it true that between two highest points, if you take the part of the wave between two crests, so this bit, you can see that in my picture, this is a convex curve. And the question is the profile convex? So these are there were two problems, and they were extremely important problems. I don't think that there was a particular great importance from the point of view of applications, but these problems were a huge challenge to mathematicians, to analysts, and they motivated a great deal in development of nonlinear analysis, bifurcation theory, and many sort of topological methods in nonlinear analysis were either invented to address this problem or they were tested against this problem. So this problem had a huge impact on nonlinear analysis. And eventually, so some 102 years later, there were two papers published simultaneously. One was by Amick Fraenkel and John Toland, and independently by Pavel Plotnikov, they proved this first conjecture. And you can see that when you have an old problem that resisted all attempts to solve it for more than 100 years, and then it eventually gets settled, then usually everything around it also gets settled. So sort of there is a breakthrough, and then people gain much better understanding of the whole variety of questions. And one probably, I guess, expected that the second problem would be solved shortly after that, which was not the case. And it took 22 more years for Plotnikov and Toland jointly this time to prove the second conjecture. So basically, they proved, I think, a little bit more than Stokes wanted, but they still believe that they have not completely solved it, because they did not, I don't think they proved that any Stokes wave with angles has this convexity property. What they proved is that they proved a little bit more than the following, that a proof of that a wave with angles, the existence was proven in 1982 for that solution. And for solutions related to it, one does indeed have the convexity, but it does not quite say that for any solution. I mean, no other solutions are known with angles, but it's not entirely impossible that there are solutions that have angles, but are not covered by the theorem by Plotnikov and Toland. Look, this is slightly sort of beyond the point, the topic of my talk. My topic is related to what happened between these two discoveries. So what happened here? And so this is, as I said, 1987 paper where Amick and Fraenkel, they were motivated by this second conjecture, Stokes' second conjecture. They wanted to study the convexity properties. And so I guess what they did was the following. People already knew that the convexity did hold in the region close to the lowest point of the wave. If I remember, it was the convexity over half the period, I think. It's just how when people, when Amick Fraenkel told them they proved the existence, the function space was set up in such a way that they knew convexity here. They did not know convexity close to the crest. And then because there was no proof, Amick and Fraenkel decided to look at the asymptotic behavior of the wave profile close to the crest. And so they studied the asymptotics of the function related, I think the angle with the horizontal direction by this profile. So they were looking at the vicinity, neighborhood of the crest, and they wrote, they derived asymptotics. And so the asymptotics is here, and this pi over 6 is related to 120 degrees, by the way. And this asymptotic is highly non-trivial. These powers, for example, they are very, very non-trivial, and they are actually related to the solutions of that equation involving tan that I showed you at the very beginning of my talk, and I will come back to this. So the asymptotic is very non-trivial, and in order to have convexity close to the crest, they actually needed to know that the first coefficient here was negative, and they themselves could not do it, I think, or at least didn't do it, and it was done by another. I mean, it was friend of Fraenkel, Bryce McLeod, and who proved that the first coefficient is indeed negative. So you do have close to the crest, you do have convexity. Right. So, and you can see that those two papers were published as companion papers. So this Amick Fraenkel paper ends at page 298, and the Bryce McLeod paper starts at page 299. So they were submitted together, the companion paper. So this is, now I'm kind of going back to the transcendental equation that I started with. I just, up to this point, it was kind of a motivation where that transcendental equation comes from, what it was related to. Okay. Oh yes, by the way, maybe, okay, it's not important for my talk, but I can't resist the temptation. Remember I told you that the importance of Stokes conjectures was that they motivated a lot in the development of nonlinear functional analysis. And then Edward Fraenkel in 2007, he kind of did something that was complete contrary to what I just said. He proved the same theorem, more or less, the existence of the Stokes wave of extreme form by very elementary methods, just by contraction mapping theorem. He kind of showed that all those sophisticated techniques of nonlinear functional analysis were unnecessary here. But I kind of cheating a little bit because he managed to do this, but because by that time, people had he himself, they had very good understanding of the behavior of those waves, how they looked like. And then people who have used contraction mapping theorem, they know that very often what you need to know, I mean, you need to set up the problem. You need to find a metric space on which you have a contraction. And because Edward Fraenkel understood very well the behavior of Stokes wave, he was able to do that. He had a very, very good ansatz to his problem. And so what I find very, very interesting, and perhaps it will be even more interesting for younger people, that what he needed to do in his paper, because it was a very, very delicate analysis there, and had a lot of integrals for which he needed sort of some estimates, inequalities. And those integrals, one could not evaluate explicitly, so he had to do numerical values of those integrals. And instead of sticking them into Maple, Mathematica, or something like that, he actually did approximate calculation by those integrals using calculated Texas Instrument TI-92 calculator. I don't know whether students can believe that people were actually doing that stuff before, but it looks like Edward Fraenkel was one of the last dinosaurs who were using machinery like this. And then there's something in his introduction where I find very, very amusing. He says that, so because of this, therefore the purists may believe that the theorems in the paper have not been proved, because he used approximate evaluation of intervals. And then when someone says this, and especially you have this word purists, you feel that the next sentence is going to be a rebuke, or I'm saying that, look, they're wrong. I had kind of rigorous stuff. The next sentence is exactly Edward Fraenkel's style. He says, well, I have much sympathy with this point of view. So, but well, he didn't need those calculations. So anyway, so this is just a sort of nice anecdote about Edward Fraenkel, but this is not important for the question we're discussing today. So let me go back to this equation. So this is the equation. This is what is important for me today. And so what they proved is that if you take roots with the real part that is greater than -1, then they're all simple and real. And say they show the asymptotics of those roots. It's not, if you look only at the real roots, you will see that this result that I'm showing you now is quite easy. Let me take you to the picture. So in blue, we have the graph of tan. I mean, tan, where the argument is multiplied by 2. So the period is what, 2. The period of this function tan is 2, and we know how the graph of tan looks like. So each blue curve here is a branch, right? And then the red is just this line. And the solutions of this equation are just the points of intersection of this red straight line and this graph of tan. And you can see that when you move to the right, this goes up, right? So the point of intersection, they go up. So the x coordinate goes to the point where tan is infinite. So this is the right end of the interval where tan is defined. So this is, so it kind of, obviously they did this rigorously, but what is behind this, you can easily see. It's just from looking at graphs. And by that time, it was known that all solutions of this equation were irrational. The proof of Grant was not very detailed, I would say, but the result is true. Although we will see that even this part is not quite as straightforward as one might think it is. Okay, so this is what they knew. And then basically, remember the asymptotics that I showed you. So the way the asymptotic was derived is kind of fairly standard thing, although it was highly non-trivial. But the method is when you have an integral, and then you move the contour of integration if you have an, say, meromorphic function. And every time you jump over a pole of your function, you gain you get a term of your asymptotic expansion. So this kind of standard thing in asymptotic analysis, but it is important to have those poles simple. If the pole is not simple, so in their procedure, a non-simple pole would contribute a logarithmic term. So their asymptotic was without logarithmic term, so they needed, they stipulated, they said that the poles were simple. In order to have those poles simple, one needs the following. Now, ZJs are the roots of this equation, so from the previous page, from here, so the ZJs are those simple roots that are real, okay? So you take those and you take coefficients that are non-negative integers. So 0 is allowed, but the sum of those coefficients should be at least 2. So you take a linear combination of those roots with integer coefficients, natural coefficients, and you add this term, okay, with 2, and so this is one set, and another set is just the set of the roots, solutions of the equation. And the assumption was, the assumption that they needed was that these two sets do not intersect. If they intersect, that we might have a multiple pole, and then you will have logarithmic terms in your asymptotics. Now they actually, again, did this maybe by the same Texas Instrument calculator, I don't know. They did a calculation that showed that if you take the first 100 terms in this set, then they do not belong to B. So basically what this says is that even if you do have multiple poles, then the logarithmic terms will appear very late in your asymptotic expansion. So the first, God knows how many 100 terms of the asymptotic expansion, they're as they are the way written by them, there are no logarithmic terms. So for any practical point of view, I guess they do know that the expansion was correct. But well, we are mathematicians, we want to have an answer to this. Are these two sets disjoint? And what they did, they stated this in a more, in a better way, I mean, in a more beautiful way, if you like. So here is the question, and this is a conjecture. So this is the conjecture. Everything what I was talking about before is an introduction. You can forget about it. So I could have started from this page. So here is the equation, and Z1, Z2, etc. are positive solutions to this equation. And so the question is this set, infinite set, linearly independent over the rationals or not? So this means that if I take a linear combination with rational coefficients, then this linear combination can be zero only if all the coefficients are zero. So is this the case? And this is still open. We don't know the answer. So what they proved was the following. First of all, not only that ZJs are irrational, they're actually transcendental. And if you take not all infinitely many solutions, but just this number 1 and any 2 roots, then these 3 numbers are indeed linearly independent of the rationals. So this is what they did. And how they did it is related to transcendental numbers. And I assume not everyone attending this talk is a number theorist. So let me take you to a brief tour of transcendental numbers. Okay, so first of all, let's define an algebraic number. So an algebraic, a number called algebraic number, I mean, it's called algebraic if it is a solution of a polynomial equation where the coefficients are integer numbers. Okay, so solutions to polynomial equations with integer coefficients are called algebraic numbers, and transcendental means that the number is not algebraic. Now, we do know that transcendental numbers exist, but I guess the first rigorous proof of that was perhaps by Liouville, who proved that this number that is shown here as an infinite series is a transcendental number. Well, everyone knows Cantor's argument that shows the existence of transcendental numbers, that the set of polynomials with integer coefficients is countable. Every polynomial like that has finitely many solutions. So the number of algebraic numbers, the set of algebraic numbers is countable. So the set of transcendental numbers is uncountable. So there are many more transcendental numbers than there are algebraic numbers, and yet proving that a particular number is transcendental is usually very, very difficult. So the kind of prehistory of transcendental numbers is that going even further back into history, Euler proved that E and E squared are irrational numbers. Lambert proved that pi is irrational number, and he conjectured that both E and pi are transcendental. And one more conjecture by Euler, he claimed, but it looks like he didn't prove it. It's a very, very non-trivial result. that if you have two rational numbers, A and B is not a rational power of A, then the logarithm B base A is a transcendental number. And this is true, but highly non-trivial. Okay, so this is like prehistory, but the true history of transcendental numbers starts in the second half of 19th century, and Amick proved that E is a transcendental number. And then later, von Lindemann proved that pi is transcendental, and he actually proved more than that. He proved that if you have an algebraic number, then e to the non-zero algebraic number, e to the power this algebraic alpha is a transcendental number, right? So so this implies that pi is transcendental number. Actually, he proved something much stronger than this, and I will come back to this, right? So so these are some of, I mean, my favorite results in the whole of math. I mean, I think they're very beautiful. And then the famous Hilbert problems, and one of them, the seventh problem by Hilbert, was that if you have an algebraic number that is neither 0 nor 1, and if you have another one, alpha, that is irrational and algebraic, then z to the power alpha is transcendental. And so this is stronger than that claim by Euler that I mentioned. And if I remember correctly, that he himself, Hilbert, believed that this was one of the most difficult problems that he stated. But it was proved in 1934 independently by Gelfand and Schneider that this is indeed the case. And this result, as you can imagine, is highly non-trivial result in number theory, and it was used by Amick and Fraenkel, who were doing fluid dynamics, and that was what they used in proving the theorem that claimed that the solutions to that equation were transcendental to this equation, and that they had linear independence for when one uses takes just two roots. Okay, so this is what they used there. Okay. Now, to go forward, let me just introduce the notion of algebraic independence. Suppose we have complex numbers, n of them, z1, etc., zn, and they're called algebraically independent if the following happens. Take any polynomial with n variables whose coefficients are algebraic, any polynomial that is not identically 0. Then you stick into this polynomial these numbers, z1, etc., zn. What you get is non-zero. If this is true for any polynomial, non-zero polynomial with algebraic coefficient, then the numbers are called algebraically independent. Now, remember I mentioned that von Lindemann proved a theorem that was just much stronger than just transcendentality of single number. What he proved was this. Suppose you have algebraic numbers. It is important that the numbers are algebraic, okay? So suppose we have algebraic numbers, alpha 1, etc., alpha n, and they are linearly independent over the rationals, okay? In that case, you put them in the exponents. So you have e to the power alpha 1, etc., e to the power alpha n, and he proved that they are algebraically independent. So this is a very, very strong statement. Now, let me show you a conjecture. It's a famous conjecture in number theory. It's called Chanuel's conjecture, and it goes back to 1960s. I think Chanuel was a PhD student of Lang's. Remember Lang's textbook in algebra? So this is that Lang, and so, oh, I mean, many textbooks. So, and Chanuel, I think, was his PhD student. So what he did is the following. This starts almost as Lindemann's theorem, but there is an important difference. We don't assume anymore that the numbers are algebraic. In Lindemann's theorem, we assume that numbers are algebraic. Now, suppose you are given any n numbers that are linearly independent over the rationals, okay? They might be transcendental. Now, if they're transcendental, you cannot say anymore that say this one. I mean, if you have a transcendental alpha 1, then e to the power transcendental power may be a rational number, maybe an integer number. So you cannot say that, like in the conclusion of von Lindemann's theorem, that these are transcendental and even more algebraically independent. But what the conjecture says is that if you take these numbers and then the powers, I mean exponentials, you have 2n numbers. And the conjecture is that at least n are algebraically independent. Now, obviously, this implies Lindemann's theorem, because if alpha 1, etc., alpha n are algebraic numbers, they cannot be a part of an algebraically independent system. So you just drop them, and the n that should exist are obviously these ones. So, of course, this is a much stronger statement than von Lindemann's theorem. Now, and this is a very impressive conjecture, and I will be surprised if someone proves this in my lifetime. I think we are nowhere near proving this conjecture. Maybe one will disprove it. This is possible, but why I'm so pessimistic is the following. I mean, basically, what people believe that Shanel's conjecture, it kind of includes all known transcendental results and all reasonable conjecture on the values of the exponential function. Basically, just to show you, look at this list of numbers. And we don't know whether these numbers are irrational. And if there is a take-home message in my talk, something that I want you to remember is that we don't know whether pi plus e is irrational or not. The only thing we know by numerical methods that this is not an integer. 2.73 plus 3.14 is not an integer. We know that this is not an integer, but for all we know, it might be a rational number. Obviously, no one believes this. I mean, I guess it's safe to assume probably that this is even a transcendental number, but we don't know whether it's irrational. Now, and for any of these numbers, we don't know this. I mean, they might be rational numbers, which nobody believes. And yet, Shanel conjecture implies not only that they are irrational, not only that they are transcendental, it implies that they are algebraically independent. So this is how strong it is. And the results that are known, they're very beautiful and very difficult, very deep. But this is the type of result that we know. This is probably one of the best results in business. So what pi, e to the power pi, and this is the gamma function. So gamma function, the value of the gamma function, 1/4. These three numbers are algebraically independent. Or pi, and so these three numbers are algebraically independent. Or pi and this number are algebraically independent. So this is what is known, but you can see that it's kind of not yet close to Shanel's conjecture. And Shanel's conjecture obviously implies this, but Shanel's conjecture is a conjecture. And this is a result. And this was considered and still is considered as a major achievement in theory of transcendental numbers. It's really very, very deep. Okay. So, and Shanel conjecture is very popular in the model theory. So it's part of logic, if you like. Remember, I mentioned that there is this kind of ranges from applied fluid dynamics to logic. And here is the part of some model theory. And top people, most people are, I mean, all of them, I think they are in Britain, Angus McIntyre, Alex Wilkie, Boris Zilva, Jonathan Pila, and Jonathan Kirby. So again, top people in this field. So Shanel's conjecture would have important ramifications for model theories as well. So it's a very, very important conjecture. Okay, now here is an advice that I heard many years ago from someone. Obviously, it's not a serious advice, but someone said that, look, if you have a problem that you cannot solve, say, for example, something to do with this equation, generalize it, and then prove a weaker version of the result that you want. So, and this is more or less what I'm going to do, not quite, but so let us look at something more general. So let us look at this equation written here, where all the coefficients A, B, C, and D, and the number beta are algebraic numbers. And beta is neither 0 or 1, otherwise you have a trivial equation. And b to power z is defined with the help of any branch of the logarithm. Okay. So, and I would like to ask the same questions about this equation. Now, this equation is more general, of course, than the equation we were talking about. And if you take these values of A, B, C, and D, and if beta is -1, then you get the exact equation that we started with. Okay, so this equation 2 is a more general equation. Okay. Now, first of all, we want to talk about algebraic independence or linear independence with respect to the rationals. So at least we need to know whether the solutions are irrational. So I come to this in a second. I will not dwell on this result. The aim of this result is to show you the asymptotics of the solutions of the roots of this equation. Remember that result by Amick and Fraenkel that I kind of explained with the help of a picture, where we had the graph of the tan curve and then the straight line, and the solutions were the points of intersections. And then we had the asymptotics of the solutions. So this is an analog of that result in this more general setting. I don't want to talk about this now. I don't have time for this. Right, so the first thing that we need to address here is whether the solutions can be rational. And for the original equation, we know the solutions are irrational. That was in the paper by Grant in 1973. And now how about this equation? Now, the first thing is that suppose you know that A, B, C, and D say belong to some number field. They're algebraic numbers. They belong to the number the field of algebraic numbers. But suppose they belong to some sort of smaller field. And so suppose there is a rational solution. So suppose there is a solution. Z is a rational number. Then you can raise both sides to the power q. The right-hand side is in your field. So, and if you have a situation where beta is such that no integer power of beta is in the field, then there cannot be rational solutions. So kind of a simple case where there are no rational solutions. This does not apply to our situation because beta is -1. Okay, so this sort of trivial consideration doesn't work here. Okay. Now, but what you can notice is that this equation is a special case of that more general one, where we have A, you see you have I times square root of 3. Now, here you have again, this I times square root of 3 is repeated everywhere. So basically the coefficients are in the so-called quadratic field with the square root of -3. And the quadratic field is just given like this. So you have a square-free number, R. In our case, it's -3. And you look at all the numbers of this, this form, and one can prove that this is a field. And the question is, so we have square root of -3. So I times square root of 3. The equation comes from fluid dynamics. Is there anything special about this case? Well, natural thing, why should there be anything special about square root of 3? Surprisingly enough, it is. And so here is a theorem that, and this equation, in the case when beta is -1, this is exactly what we have. And if the coefficients belong to a quadratic field, then the rational solutions can only exist in the following 3 cases. Now, first of all, you might have a sort of very special case where there are integer solutions. It's kind of not interesting in that case. We can have a solution where we don't have like square root of 3, we have just I there. Again, it's not the case we're looking at, and just the only remaining case when you have you can have rational solutions is when you have square root of -3. So it is a special case, and this, well, although I kind of sort of put my name here, the result is you cannot say that it's my result. It's just I wrote it down. It follows in an almost trivial way from a classical result of units, of quadratic fields, and you can find it in the work by Hilbert. This way I found it. Okay, so it's a kind of not a very deep result, but the consequence is here. So although this equation that we're interested in, it does not have rational solution. I mean, it's a proof of this, and maybe Grant has a very short proof and not complete, but there's a complete proof. It's not difficult, so it follows from that result on the previous page. But if you just change this 1 for 2, now this guy has a rational root. So basically, the whole conjecture by Amick and Fraenkel could have been spectacularly wrong if in the equation it was not just 1 but 2. The square root of 3 is special. But if you substitute it by square root of 5, then whether you have 1 here or 2 there, you cannot have rational roots. So there are no rational roots for this equation, but this equation is this close to having rational roots. So this is one thing. Another thing, so for this equation, we have an exact analog of the theorem, by the main theorem by Amick and Fraenkel on transcendentality of solutions and on linear independence of 2 roots. So suppose you have solutions that we know are irrational. So, okay, we kind of have already addressed to some extent the case where we know when there are no rational solutions. So suppose this is given. Then each solution of this equation, more general, is transcendental. That's the exact result by Amick and Fraenkel in the special case. And then if you have this strange condition satisfied, this one, then you have the same conclusion as in Amick and Fraenkel theorem, that you have linear independence. However, if this equality is satisfied, then the exponent here is a rational number, and together with Zj, this number is also a solution. So you do have linear dependence, but this is the only way you may have linear dependence. So if you take 2 different roots, and one is not this combination of the other one, then they are linearly independent. Okay, so we know that we have this conclusion in the case of Amick and Fraenkel. So therefore, it's kind of safe to assume that this is what they have, right? Wrong. What they have actually is the case of equality. And but this doesn't mean that the result is wrong, because look, what if Z1 is a solution, then, well, it follows from the theorem that this is also a solution, but obviously you don't need that theorem to make this conclusion. You just stick this into the equation and you see that this is the case. This does not mean that the theorem by Amick and Fraenkel was wrong. They simply didn't look at all roots. They looked only at positive roots. And for positive roots, this is exactly what happens. Now, point here again, this is a second instance where the conjecture was that close to being wrong. So somehow this equation coming from fluid dynamics hit 2 singular cases. I don't know why this is the case. I mean, some miracle. Okay, now what can we say in the general case? Not much. The result is conditional on Schanuel's conjecture. So it's not a true theorem like this, it's a conditional theorem. So if we have irrational solutions, distinct irrational solutions, and suppose we know that for every pair, these 3 numbers are linearly independent of the rationals. And the previous theorem tells you exactly when this happens. So kind of these conditions are fine. There is nothing wrong with this condition. However, the conclusion is that if Schanuel's conjecture is true, then not only the conjecture of Amick and Fraenkel is true, it actually much stronger thing, that these numbers are not just linearly independent with respect to the rational, they're actually algebraically independent, okay? And so this is where we are. It's not kind of a true theorem, but it, in number theory, there are many results that are conditional, say, for example, on Riemann hypothesis, and there are many results also in transcendental number theory that are conditional channel conjecture. So kind of this theorem just adds to those lists. Now, and I know that my time is running out, so I probably need one more minute. There is a result that is completely unrelated to what I was talking about. It's about maximal functions, and by this paper, beautiful paper by Stefan Steinberger, and a similar equation, but simpler. You have tan of x equals x. But somehow he needed similar results that, and he proved that x is transcendental and x and pi are linearly independent of the q, and any two elements are linearly independent of the q. And this is slightly simpler than Amick and Fraenkel result. And this is, I think he uses von Lindemann theorem rather than Gelfand-Schneider theorem. So it's kind of more elementary. But nevertheless, again, it's kind of miraculous that the same language, the same type of problem arises somewhere completely unrelated. And I finish by something that I really kind of, by bragging. So there is a recent book on transcendental number theory, and I consider this my second highest achievement in maths. I found myself quoted in a chapter on exactly Gelfand-Schneider theorem. So this equation now, Amick Fraenkel conjecture, appears as an exercise there, that result. And I'm most proud of being quoted next to Nesterenko. Nesterenko is a true great mathematician in number theory, and I kind of being next to him makes me immensely proud. I stop here.
Thank you very much, Zhenya, for a very nice and very, say, uninspected talk. My question is, how do you come to this topic?
I was Riemann-Hilbert Topliss operators, Riemann-Hilbert problem. Riemann-Hilbert problem, I started collaborating with John Toland on Stokes waves. And in Stokes waves, I knew about, I read somewhere there was a result, unproven result in number theory. I just looked at what that result was. And because I knew that neither Edward Fraenkel nor Amick were number theorists, I thought, oh, maybe they didn't know what they were doing. And it was naive of me. They knew very well what they were doing. I thought maybe no proper number theorists looked at that. This is also wrong. I think that Edward Fraenkel asked Alan Baker, and Alan Baker is the person who probably contributed to transcendental number theory more than anyone else. And he got Fields Medal for transcendental number theory. And Edward Fraenkel asked him, Alan Baker was not able to reply on the spot. I don't think whether he spent like even 15 minutes after that, this I don't know. But when I started working on this, I didn't know that Fraenkel asked Alan Baker, because had I known this, I would not have touched this at all. Because, and this is how I sort of came to this. And yeah, I had a lot of fun doing that. I mean, you know, they say that every analyst is a failed number theorist. Now I consider myself semi-failed, not completely failed.
Well, your paper is dated 2014. Are
Yes.
you still working on this?
Not really, no. I think, look, I'm the wrong, I mean, I only scratched the surface, but I have to say, I was joking about this page that you can see, but basically, it's not, there was something serious about this too, because I believe that this number theorists might actually do something on this particular problem. Whereas channel conjecture is hopeless, I think. This one, and I mentioned Angus MacIntyre, who is in model theory, but also number theory. And he believes that this particular problem might be at the border of what number theorists can do. I mean, some number theorists, as you can see, they see this. And actually, Matt's review on this paper of mine was written by someone who is a top expert on transcendental number theory, and he didn't say that it's trivial, etc. But so the result, so the conjecture is still open, but this conjecture might not be beyond the reach of what people know. I mean, if someone just announces the proof of it, I will not be surprised. I will be very surprised if someone announces the proof of Chanel conjecture, though.
Okay. More question, comments?
Yeah, there's a question.
Yeah. Wolfram, I want to tell something.
No, it was.
I think there was someone before me asking. I have a very naive question, but
Yes, please.
I think I'm not next. There's
Who's next in questions?
Yeah, sorry, can I ask something?
Yeah, sure.
I just want to say thank you for this nice talk. It's a little bit complex for me, but it's very interesting. And I just want to say thank you for everything and for sharing knowledge.
Thank you.
So what happens if you replace tangent by cotangent? Is there anything, does that have any meaning?
It might.
Equation.
It's probably, and I will not be honest answer, I don't know, but I suspect that it will probably come to this form.
Another special case of this one.
Yeah, I don't know this for sure, but it's kind of, I wouldn't be surprised if this is the case.
But very, very beautiful talk. And so what's your opinion about Chanel's conjecture? Do you think it's true or not true? Do you have any
you know what,
intuition about this?
I don't, but I asked the greats. I asked, I asked Angus MacIntyre and I asked Alex Wilkie. And Angus MacIntyre, I think he believes that he says that it might be true because, you know, if it is not true, there should be some identity involving E that is completely different from anything that we have ever seen. It's a completely new algebraic identity involving E, which kind of hard to believe. On the other hand, Alex Wilkie, I asked him, and he said, you know, maybe for one or two numbers, like, you know, in the conjecture you have alpha 1, etc., alpha n. He said for low n, the conjecture is probably true. But he said, I don't see why for large numbers, if you have many numbers, why it is still true. It might not be true, he said. So I don't think that people who actually know about this stuff more than anyone else, they have sort of strong beliefs about this. It's very difficult to say, but you know what? Say this sort of result that I showed, right? So the conjecture, Amick Fraenkel, I like it, but it's not kind of the most important conjecture in math. So, so if Chanel conjecture is true, okay, it implies everything. And this Amick Fraenkel conjecture is probably one of the least important conjectures that will fall. But suppose that there is no algebraic independence of solution for this equation, then you disprove the Chanel conjecture. So maybe the only value of this theorem may be if someone kind of produces counterexample for this equation too, that will kill Chanel conjecture then.
Mm. I see.
But I don't think it's very likely though.
So I don't know much about these things, but I think there's also the conjecture about the linear independence of the values of the Riemann zeta function at odd integers, for example. Does that have anything to do with this general conjecture, or is it a completely different story?
I think it is a different story.
Completely different.
No, well, no, not quite. No, well, no, the answer is I don't know. I suspect that probably not quite, but there are conjectures involving elliptic functions, for example, that are related to this stuff, but not perhaps zeta function itself.
Other questions, comments, please? If not, thank you very much again, Zhenya, for very beautiful talk and very surprising, I would say, because I never believed that you might enter to this so specific field.
Don't worry, I left it. I left the field. Just a very brief incursion.
Well, we will have the third day tomorrow, and we will have two talks by Grigory Rosenblum and Wolfram Bauer. So hope to see you tomorrow, and bye for now.
Bye.